Practice question set number 31 starts off with 3 reactions. And the first question asks us to classify the first reaction. In the first reaction, we have hydrogen 1 and hydrogen 1 coming together to form hydrogen 2. That's 2 light nuclei forming 1 heavy nucleus. That's what kind of reaction? Yeah, that's fusion reaction, since small nuclei make a larger nucleus. Now, this is not the reaction that we looked at in class, not the specific one that we looked at in class, because here you have a positron produced, right? And a neutrino produced. So this is not the reaction that we looked at in class. That's okay. That's okay. It's not the exact reaction that we want to remember. It's the structure of the reaction that we want to remember. In the end, this is the same structure where we have 2 light nuclei forming 1 heavier nucleus. So the answer is A. 2, which the following statements describes the total measured mass as represented on the left side versus what's on the right side. This is reaction 2. Doesn't really matter though. Reaction 1, reaction 2, whatever. On the left side, what do we know about the mass compared to the mass on the right side? The left side is bigger. We lose mass. What's that missing mass called? Mass defect. And that would translate to the energy equivalent of that would be what we call the binding energy. So we're going to say the mass on the left is greater because of the energy equivalence of the mass defect. The answer is D for that one. Right, Josh? Third question. Numeric response number 1, we see a Venn diagram here. You guys know what a Venn diagram does, right? It describes what different things have in common or don't have in common. Here we're trying to describe what fission and fusion have in common and don't have in common. If it's number 1, then the property belongs only to fission. If it's number 2, it belongs only to fusion. And if it's number 3, it belongs to fission and fusion, that property. What about number 4? Neither of them, right? It's neither fission or fusion. So let's match the numbers of the regions in the Venn diagram with the descriptions given below. The measurable mass of the products is less than the measurable mass of the reactants. In other words, we have a mass defect. Is that fission, fusion, both, or neither? That's both, and that's going to be 3. The kinetic energy of the system increases as in a spontaneous reaction. Fission, fusion, both, or neither? That would be both. And we described those equations, and in both of them, we had energy produced on the right-hand side, and we said that that energy is roughly enough. It's different depending upon which kind of reaction we have, but roughly enough to move a speck of dust. Well, what kind of energy does the dust have when it's moved? Kinetic energy. Right? So the kinetic energy of the system increases for both of them. The third one here, uranium-236 goes to krypton and barium. What kind of reaction is that? That's a fission reaction, which is reaction number 1. Now, this looks different, right? It's still 1 heavy becoming 2 lighter nuclei, but we don't see a neutron on the left-hand side there. Notice that? We don't need it this time. How come? This is a spontaneous fission reaction. It's a spontaneous fission reaction because we already have uranium-236. Remember we said in the example that I gave you in class, we bombard uranium-235 with a neutron, which temporarily becomes uranium-236, which decays into a couple of different possibilities. If we already have uranium-236, then we don't need to bombard it with that neutron. So the reaction that we described was an artificial one, the one that we made happen. This would just be a natural fission reaction. But it's still, any way you look at it, it's still 1 heavy nucleus splitting apart into 2 lighter nuclei. It's still fission. And the last one, uranium-236 goes to thorium-232 and an alpha particle. That would be what? That's radioactive decay, right? That's just alpha decay. So that would be neither. Okay? Somebody in the last class said, well, I got confused because that's 2 lighter nuclei, right? 1 heavy, 2 lighter nuclei. That's a good point. That's a really good point. 1 heavy, 2 lighter nuclei. But if one of those lighter nuclei is a beta particle or an alpha particle, okay, then we're going to define it based on the specifics that we talked about at the beginning of that section, which is alpha decay, beta decay, whatever. Okay, so that is alpha decay. The answer for that one is 3314. Rutherford's planetary model of the atom had to be revised because Maxwell's theory of EMR, Maxwell's theory claimed that, well, did he claim that charges at rest release EMR? Absolutely not. Charges at rest produce an electric field, that's it. Accelerating charges produce EMR, do they? Yeah, he said that they do. So that seems like it works. Let's just double check the rest of them here. Accelerating charges do not release EMR. No, he said that they do. Right, Max? Charges traveling at a constant velocity release EMR. No, he said they produce an electric field. They also produce a magnetic field, but not a changing electric and magnetic field. And we need changing electric and magnetic fields. So it would be accelerating charges generate EMR. What kind of acceleration do these electrons experience as they go around the circle? Centripetal, because it's an acceleration toward the center of the circle. And finally, number 4, we got this little experiment taking place where the teacher's throwing beanbags at students. I thought this would be better if the teacher had one of those, like, you go to a hockey game and they have those t-shirt guns, and the teacher fired like those balled up t-shirts to the students. But anyways, she's throwing beanbags at students, and we want to simulate a Rutherford gold foil or a Rutherford alpha scattering experiment here. What would the beanbags represent? The alpha particles. And what would the students represent? The nuclei, right? The nuclei of the gold atom. So the answer for that one would be